This is Dylan Sieverts going over quiz number 7. And basically it's is this quiz number 7? Oh yeah, it is. The wire wrapped around a disc with a radius and a mass, and we know that it's released at rest. So to set it up, I basically just drew my free body diagram. We know that there's a weight of the disc acting on it and going downward, and we know that there's a velocity. The VG should technically be down here. And we need to figure that out, but and there's also this tension. So basically I just put my kinetic energy and my potential energy for position 1 and position 2. My potential energy down here is 0, because I would assume it stops. I did have to make quite a few assumptions on this, and I'm not sure if they're accurate. That was one of them. And then my kinetic energy up top is 0 because it starts at rest. My potential energy for the entire system from point 1 to 2 is going to be the weight times the distance times gravity, pulling it down. So that's basically the work done from gravity. And then I needed to calculate my kinetic energy at point 2. And so linearly, when this wheel moves down, I can use my linear kinetic energy formula, which is 1/2 mv squared, and that's due to gravity. However, once that moves, this wheel starts rotating. This way, I had it right. So then it gets a linear velocity, a rotational angular velocity, is because it's tied to that rope. And so what I did is I accounted, right here, I accounted for the kinetic energy with the rotational kinetic energy, and I'm not sure if I still need to account for tension, because I'm not doing the sum of forces in the x and y direction necessarily. I'm just doing what's happening at point 2. So I would assume that since the tension is directly converted into rotational energy, that we don't have to take into account for tension up there from the rope. So this is 1/2 I omega squared. However, we know our moment of inertia, I, for a thin disk, which is right here, and based upon looking at the photo, it's rotating about the x. So we would take the Ix formula, which is 1/2 mr squared, and we would plug that in. And then omega, that's a velocity, but it's in rotational, so we need to convert that too linear because that's what the question is asking. The velocity of the center of the cylinder after it's moved downward. So that's just velocity over r, v over r squared. And then we square that because omega is squared. And then we just plug all of those items in and solve for our tension at point, or not tension, our kinetic energy at point 2. And so we know that's the change in kinetic energy because the kinetic energy up here was 0. So that's the work done. And so that has to equal, or that's the change in the system basically from potential energy, and that goes to kinetic energy, which we just solved for. So then we can just set those equal to each other since T1 is 0. We know this and we know this. And this is right here is where we plug it back in. So mg times the distance, which is the work done by gravity. And then we got 3/4 mv squared for the kinetic energy. And then we just solve for velocity. And that's in the downward direction. It's square root of 4/3 g for gravity times s distance. And that is downward, so I'm not sure if you want us to do minus or not, or just put the direction, but that is what I got.